This presentation is an overview on maximizing mine production at your quarry, whether the product is cement, aggregates, clays, diatomaceous earth, or other industrial minerals. It is also applicable to metal mining operations. My name is Paul Hartley, and I'm the manager and one of the geologists at TerraSource Software based in Reno, Nevada, and I have experience in industrial minerals and metals exploration and production. I've been working with Dassault Systèmes products for the past 20 years, primarily GEOVIA Surpac, Mineshed, and Whittle. Using a limestone deposit as an example, we'll step through the major tasks in modeling, planning, mining, and producing from the quarry. We'll identify those tasks where you measure, where you estimate and model and plan, and where you compare and refine the estimated model and plan. As quarry managers, mining engineers, and geologists, your objective is to deliver the right material at the right time to the right place at the lowest cost over the life of the mine. As I mentioned, we'll review the task in the mining cycle where you measure, where you model, where you plan, and where you can adjust. If there's feedback into the model, then the model, including the schedule and the plan, become more refined, more accurate, and more useful. The major tasks in the mining cycle include exploration. This is primarily a measurement step. In general, the more samples collected, the more information about the target that is collected, the more accurate the model will be. Resource modeling is the first of the estimations, and all decisions are based on this model. Pit optimization is a modeling step based on the resource model and best estimates of mining and processing costs. For deposits with significant dips or with complex ores, an ultimate pit can be defined by the pit shell with the ultimate MPV. For relatively simple shallow dipping deposit, this task may not be necessary. Mine design uses the optimal shell if it is available and the resource model to build a practical, mineable quarry. And scheduling takes the design and model and produces a long-term plan to deliver the right material to the right place at the right time. The next steps are within the quarry. Drill and blast is where blast holes can be designed to the optimal pattern for each material type. You can use the designs to accurately estimate the cost of equipment and blasting supplies. Grade control. If analyses are run on the blast hole cuttings, they can be used for grade control. Using the analyses, a production model can be estimated, and the schedule, which can be adjusted if there are significant differences between the exploration model and the production model. Lastly, haulage can be estimated in the initial schedule, measured each day, and then compared between planned and actual. The final steps are completed outside of the pit. Stockpiling. This is the intermediate step before blending. In setting up the schedule, stockpile grade cutoffs are determined by the resource model interpolated values. Blending of the stockpiles can be planned in the scheduled task. This provides the opportunity to minimize the amount of wasted material. And then once the end product is generated, reconciliation can occur with the production model and with the stockpiles. Using the previous task as backdrop, this slide identifies which tasks are measurements, estimations, and comparison steps and adjustment opportunities. A set of Dassault Systèmes applications provide the tools to make the measurements, estimations, and comparisons. These tools include the geological modeling and mine design packages called Surpac and GEMS, Whittle for pit optimization, and Mineshed for production scheduling and target blending. Everything is built upon the original measurements, the drilling and sampling of a prospective geologic area. Spending 1 to 5% of the total acquisition and development cost of a deposit on drilling and sampling is a good investment. It is the first and most critical of the measurement task. There are approximately 4,000 meters of drilling in this example. This deposit consists of 2 limestone beds, and the upper bed containing higher magnesium values. The two beds are separated by a high silica bed. Geological modeling is the 3D interpretation of the drill hole results along with any other sources of information. For example, surface geological mapping. The two limestone beds are in two shades of blue and are locally separated by a chert lens. These cross-sections are 100 meters apart and we are looking towards the east. Each section is interpreted and the resulting geological model is then applied to the 3D grid, the block model. The analytical values from the drill hole samples from each bed are interpolated into the blocks that correspond to those beds, using only samples from a rock type to estimate blocks of that rock type. Derived values such as C3S and lime saturation factor can be calculated from the block model grades. This overview shows the entire block model below topography. Overburden is in yellow. The two limestone units are in blue with the chert lens in red. The footwall shale is in brown. In this example, each block is 5 meters by 5 meters by 5 meters. In each block there are multiple attributes, one for CAO, one for MGO, etc. The actual values for each attribute are interpolated from the block drill hole analyses. Although a pit optimization was run on this example, with the relative thinness of the overburden, shallow dip of the limestone, and thickness of the limestone beds, the optimal shell was simply pushed to the limits of the property boundary. Based on the geological model, property boundary, and waste dump size requirements, the mine and dump designs are created. These designs define the blocks to be mined and the blocks to be used in the mine planning and long-term scheduling. We are approaching from the west. The waste dump was on the right, and we drive down the haulage road to the bottom of the ultimate pit design. The long-term production schedule is developed from the blocks within the pit design. The long-term schedule usually covers the life of the mine. Reasonable rates of mining, restricting the number of working faces and benches to a realistic number, using grade targets for stockpiles and targets for blending to the process plant are all inputs into the schedule. This animation shows the blocks to be mined by period over the life of the mine. The pit is to the left and the waste dump to the right. Each of these colors represent a specific time period. In this case, a period is 3 months. If the plan is followed, the right material can be consistently produced over the life of the mine. The only caveat is the accuracy of the block model. The model can be reassessed and updated if necessary by checking against blast hole samples and reconciling with produced material. We've briefly stepped through the planning steps. Now into the mine, including drill and blast, grade control, using production grade information, adjusting the short-term schedule, and estimating and measuring haulage. These blocks are the interpreted rock units for one bench. The blocks are colored by C3S values, an attribute that is calculated using CaO, SiO2, and other oxides. The red blocks are overburden, and the orange blocks model the chert bed. The yellow, light green, and blue areas are limestone blocks colored by C3S values, with the higher values in cooler blue colors. These lines are the outlines of the chert, upper limestone, and lower limestone. Using the blast design tools and blast patterns specific to each rock type, an optimal number of blast holes can be calculated. For example, blast hole spacing in the chert bed could be wider since the material will not be crushed and will be wasted. The drill and blast tools can be used to report the amount of drilling, the amount of explosives, the number of boosters and detonators. In addition, If analyses are run on the blast hole cuttings, sample numbers can be generated for the lab. Analytical results of the blast cuttings allow for grade control. Blast holes will create a large number of samples over the life of a mine, and tools are provided to handle the data, including generating sample numbers for the lab and to reload the results once completed. The analytical results in the blast holes are color-coded, and then dig lines are drawn. Waste material is taken to the dump, and medium and higher C3S material is taken to separate stockpiles for blending. If block sizes are roughly the same as the blast hole spacing, approximately 5 meters in this example, the blast hole grades can be interpolated into the block model, and comparisons can be run between the estimations from the exploration drilling and the blast holes. If the block size in the resource model are significantly different than the blast hole spacing, a separate production block model may be necessary. In this example, the blast holes show a plus or minus 5% difference with the resource model results. The closer the values are over an extended period, the greater confidence there is in the initial resource model. If there is a large difference, additional fill-in exploration holes should be considered. A short-term schedule, in this example 12 one-month periods, can easily be made. The top chart on the left shows tons removed from the pit. The bottom chart outlines truck hours for waste tons in green and ore tons in tan. The charts are useful for identifying anomalies in the schedule. For example, the total number of truck hours for period 2 is much higher than the average for all 12 periods. Perhaps it can be evened out by tweaking mining locations, but since it mostly involves moving overburden, the additional hours may be required to meet ore production goals in subsequent periods. The planning can estimate the truck hours for each 1 month period for all haulage of material to the stockpiles and plant and to the waste dump. If actual truck hours are significantly different from the model, then either the model is a poor estimate and it needs to be adjusted going forward, or there may be something amiss. For example, trucks that are not loaded to capacity, excessive waiting time, excessive maintenance downtime, or other scenarios when trucks are not hauling ore or waste. Measure the actual, compare with the planned, and adjust if the actuals are outside of an acceptable range from the planned. We've touched on each of the pit tasks, and the remaining steps are stockpile, blending, processing the material, and reconciling what is produced versus what was expected. These are the blocks to be mined in 12 one-month periods. This diagram outlines material movement from the pit to the 3 stockpiles, from the pit to the waste dump, and from stockpiles to the plant. A target of 130 C3S value is selected for the plant. This is a chart for the plant. The right vertical axis are C3S values. The left axis are tons, and the x-axis are each of the 12 one-month periods. The top flat line is the targeted C3S value of 130. The green line is the planned based on the schedule, and the tan bars are the planned tonnages moved to the plant. Because of overburden removal during the first period, there was insufficient ore material available for the plant. The closer that the actual is to the planned, the more confidence you will have going forward. If the actual production and grades are significantly different than the planned, adjustments to the model, perhaps as simple as adjusting mining direction or number of mineable benches per time period, are required to increase accuracy and confidence. The earlier it is done, the more time there is to adjust and maximize the production and minimize waste over the life of the mine. In conclusion, if you measure, you can model. If you model, you can estimate. If you estimate, you can plan. If you plan, you can reconcile. If you reconcile, you can improve.